Welcome. Today's explainer is all about demystifying a truly revolutionary piece of technology. For decades, computers were just counting words, literally treating them like isolated math problems. But today, we're going to explore the exact architecture that taught machines how to actually understand them, mapping context just like you and I do. Let's get right into it. Here is our structural roadmap for today. We'll start with the problem of context, enter BERT, the magic of attention, how BERT learns, putting BERT to work, and finally, we'll wrap up with its legacy and limitations.
Section 1. The problem of context. Human language is incredibly messy, inherently ambiguous, and heavily reliant on what surrounds a word.
So let's start with a relatable little puzzle. Think about the word bank. To a human, it's instantly obvious what this word means depending on the sentence it lives in. But to a machine, well, B-A-N-K is just a string of characters. How on earth does a computer know if you're talking about depositing a check or sitting by the water?
And this brilliantly illustrates our core problem. Take these two sentences. The bank approved my loan versus the riverbank was muddy. Older natural language processing models, like Word2Vec or Glove, usually assigned one single fixed mathematical vector to the word bank. So they effectively blended a financial institution and the edge of a river into one incredibly confusing concept. They treated words like static dictionary entries, not like dynamic actors whose roles completely change depending on the scene.
Looking back, we can actually see how this builds historically. In the 1950s, we had bag of words, which literally just counted words as if they were items dumped in a bag, ignoring grammar entirely. By the 70s, TF-IDF helped weigh the importance of certain words. Then in 2013, Word2Vec gave a static similarity, so it knew king and queen were related, but it still gave each word one fixed meaning. By 2018, a model called ELMO finally introduced contextual reading, but it read sequentially, step by step from left to right. And then, later that same year, everything changed.
Section 2. Enter BERT, the context revolution. This is the architecture that fundamentally rewired how we build natural language processing systems.
Okay, let's break down this heavy acronym. BERT stands for bidirectional encoder representations from transformers. I know, it sounds super intimidating, but the core idea is remarkably elegant. It's a transformer-based model that reads a sentence from both sides at the exact same time. Instead of reading left to right like a human reading a book, BERT looks at the entire sentence at once to create a deep mathematical understanding of what every single word is doing in that exact specific context. So, instead of acting like a static dictionary, think of BERT like a detective. Before deciding what a word means, it hunts for clues by forcing that word to look at every other word in the sentence. It lets the surrounding context define the word rather than the word defining itself. Section 3, the magic of attention. Words talking to words. Let's look at the specific mathematical mechanism that makes this deep, web-like reading possible. Take a simple three-word phrase, not good. A weak, older model might spot the word good, count it, and predict that this sentence has a positive sentiment. It completely misses the structure. But BERT uses something called self-attention. Self-attention allows the word good to look directly backward at the word not. The model sees that not modifies good, allowing it to instantly flip the sentiment and understand the overall negative meaning of the scene. It's a total game changer. And BERT doesn't just do this once. It has multiple attention heads. You can think of them as a classroom of highly specialized students all discussing the sentence together. One attention head is the grammarian, finding subject-object links. Another is the critic, linking emotions to nouns. Another is the contrarian, looking for negation. And another is the detective, figuring out exactly which noun a pronoun like it refers to. They process all these relationships simultaneously, turning a linear sentence into a rich, interconnected web of meaning. Section 4. How BERT learns. Filling in the blanks. If that is how it reads, how do we actually teach a machine to do that? Well, to teach BERT to be such a careful reader, researchers used a brilliant technique called masked language modeling. Imagine a student taking a fill-in-the-blank test. During training, researchers literally masked certain words in massive amounts of text and forced the model to guess what was missing. For example, the student opened the blank and started reading. To solve this puzzle, BERT has to rely on bidirectional deduction. It looks at the left context. The student opened the, which suggests an object. Then it looks at the right context and started reading, which suggests a text. Together, those clues from both sides point directly to the word book. Older models that only read left to right could only guess based on the past. BERT uses the past and the future of the sentence to deduce the present. Section 5, putting BERT to work, from learning to doing. Now that we have a highly trained, context-aware machine, how do we connect this architecture back to the real world? First off, we need to clear up a massive point of confusion in the AI space, the difference between BERT and GPT. BERT is an encoder-only model. It's the careful reader. Its job is to deeply understand and map the input text you give it. GPT, on the other hand, is a decoder-only model. It's the excellent writer. Its architecture is built to predict and generate brand new text output. Basically, you use BERT when you need to understand something deeply, and you use GPT when you need to write something new. In the real world, developers use a highly efficient pipeline. Step 1 is pre-training, where BERT reads massive amounts of text to learn general grammar and facts. Step 2 is fine-tuning. Instead of building a completely new model from scratch for every single task, developers take this pre-trained BERT brain and train it just a little bit more on a specific labeled dataset. Finally, in Step 3, this fine-tuned model is deployed to perform specific applications, like analyzing the sentiment of movie reviews, identifying names and locations in legal documents, or even powering the search ranking algorithms you use every single day. Section 6, Legacy and Limitations. Taking an impartial look, it's important to see where this architecture falls short and what evolved from it. We definitely must note that BERT is not perfect. It's computationally very heavy and requires massive memory compared to older models. It also has a strict 512 token input limit, meaning you can't just feed it a whole book at once. You literally have to chop the text into chunks. And, as we established, it's not designed for open-ended text generation. For simple, keyword-heavy tasks, older models might actually be a faster, cheaper choice. It's also worth pointing out that, like many models, it can inherit social and linguistic biases directly from its training data. However, BERT's true legacy is that it acted as a bridge to modern AI. It proved absolutely that attention-based bidirectional understanding works. And it spawned an entire family tree of descendants. Roberta optimized the training process. Distalbert made the model smaller and faster for production. Albert made it highly parameter efficient. SentenceBERT optimized it specifically for semantic search. And domain-specific versions like FinBERT for finance and BioBERT for medicine proved that you could teach this careful reader the specific jargon of literally any industry. Which leaves us with this final thought. BERT shifted machines from merely counting our words to mapping the intricate webs of relationships between them. It taught computers that context is everything. So if machines can now map these relationships as well as we do, how will that change the way they interpret everything we write in the future?